Chapter 7. Fields, Electrodynamics in Chapters 4 through 7. Classic electromagnetism (EM) is covered, with extensive coverage on the Lorentz transform. EM is Lorentz invariant, in Ch8, which then leads to special relativity and general relativity and other topics in later chapters. This chapter, Ch7, is the last of the main EM sequence and is on dynamical electromagnetic systems in general, with careful analysis of frequency dispersion effects as well as broadcast/radiation and surface/interface problems, transmission lines, microwave waveguide. The material draws from Jackson chapters 6-9, Ramo chapters 5-12.
Note on examples and exercises. The chapters on electromagnetism draw, foremost, from the excellent source, Classical Electrodynamics by J.D. Jackson. That was the required text for many years at Caltech. Many of the Jackson problems developed the physics theory further, e.g., Gauss's theorem, or further developed the mathematical techniques, for ODEs, definition of delta function as limit, etc. With my own notes from the courses at Caltech, and upon later preliminary exam review at the Universal Wisconsin, the addition of the completed problems from various sources were acquired in a way that seemed to provide a mapping of understanding. I wanted to convey that understanding here. Solutions to these key problems are carefully worked out in what follows, along with notes on the theory from Jackson as well as from. Basic exercises are given to rederive or verify the theory. The solutions to the exercises here, for the most part, are available via the aforementioned Jackson text, with the detailed derivations provided there.
Many examples and related problems are done in order to cover material from basic undergraduate problems to advanced engineering for antenna design, say. So the notes and problems also draw from undergraduate and graduate EM class notes/exams, and the other texts mentioned. The remarkable success and modern applications of EM will be made evident, but at the end of Ch7, when we carefully analyze the hydrogen atom, we will find that there is radiative collapse in the classical theory. This fundamental flaw in the theory, when dealing with even the simplest bound atomic system, will be corrected with the development of the quantum theory in Book 4.
7.1 Time-varying EM fields. Faraday's observations of time-varying electromagnetic fields, in mathematical terms, will be done now but with direct mathematical expression according to Maxwell. Given that the magnetic induction in the neighborhood of the circuit is B. Define the magnetic flux, linking the circuit by equation 7-1. The electromagnetic force around the circuit is equation 7-2. Where E' is the electric field at dl in the coordinate system where dl is at rest. Faraday observed that, equation 7-3. The sign is specified by Lenz's law, which states that the induced current, and accompanying magnetic flux, is in such a direction as to oppose the change of flux through the circuit. Determination of the constant k by using Galilean invariance, x' equals x plus vt, t' equals t, in the appropriate non-relativistic limit.
Equation 7-4. Since dB over dt' equals the fraction with numerator partial differential b and denominator partial differential t' plus v dot gradient sign with over it, times b equals the fraction with numerator partial differential b and denominator partial differential t' plus gradient cross, b times v prime, plus gradient sign with over it, gradient.b. With gradient.b equals 0, this becomes. See the next equation. Or see the equation shown in the lab frame where E is the field in the lab frame. Equation 7-5.
Galilean invariance yields the fraction with numerator partial differential and denominator partial differential t equals the fraction with numerator partial differential and denominator partial differential t prime, etc. Due to assumption of absolute time, this implies in turn that the RHS of the two equations are equal, thus the LHSs, so, equation 7-6. In order to determine k, merely consider the significance of E'. In prime frame, force experienced on charge is QE'. In lab frame, charge represents a current J equals QV delta times x minus x sub 0, and so from the magnetic force law, dF equals the fraction with numerator I sub 1 and denominator C times dL sub 1 times B, or F equals 1 over C, the integral from 2 of J times B d cubed x. So we see that the charge, current, experiences an additional force, aside from QE. In agreement with Ampere's law of K equals 1 divided by C in Gaussian units.
In Gaussian units, Faraday's law therefore reads, equation 7-7. As A byproduct, we have found that the electric field E' in A coordinate frame moving with A velocity v relative to the laboratory is equation 7-8. Interestingly, even though derived using Galilean invariance, v is much less than c, the result is valid in the relativistic formulation as well, and is known as Lorenz's law, equation 7-9. Holding the circuit fixed in a chosen reference frame, in order to have E and B defined in the same frame, Faraday's law can be put in differential form by use of Stokes' theorem to get the differential form of Faraday's law. Equation 7-10.
In the integral form, and more obviously in the differential form, we have a far-reaching generalization of Faraday's law. The circuit can be thought of as any closed geometrical path in space, not necessarily coincident with an electric circuit. In the differential form, of course, there isn't even a reference to a circuit. Energy in the magnetic field. Determining energy in magnetic fields is not as simple as the energy in an electric field, since we can't analogously fix the charges and make a simple build-up. The creation of a steady-state configuration of currents and associated fields involves an initial transient, during which the currents and fields are brought from zero to the final values. For such time-varying fields there are induced electromotive forces which cause the sources of current to do work. These contributions must be considered when describing the energy of the field, since the field is by definition the total work done to establish it. Consider a single circuit, current I. If the flux through the circuit changes, there is an E induced on the circuit. If the current is kept at I, work is done dW over dt equals negative I equals 1 over CI dF over dt. Work done by sources. Thus,
equation 7-11. Break up current distribution into a network of elementary current loops, elemental tubes of cross-sectional area triangle sigma, then equation 7-12. Since J triangle sigma dl equals JD cubed x, by definition, equation 7-13, and use gradient cross H equals 4 pi over Cj. Equation 7-14.
Since we have a localized field distribution, the last term is 0, thus, equation 7-15. Where, in this form, the relation is also applicable to all magnetic media. If medium is para or diamagnetic, we have a linear relation between H and B, so equation 7-16. For which equation 7-17. Magnetic energy change in energy when an object of permeability mu sub 1 is placed in a magnetic field whose current sources are fixed, equation 7-18.
Thus, equation 7-19. Example 7.1. Consider a system of current-carrying elements in empty space. A. Show that for current density J of x, the total energy in the magnetic field is. See the next equation. B. For n circuits, each with their own current I sub n, show that energy can be expressed as see the equation shown. Solution. A. System of current-carrying elements in empty space. The total energy in the magnetic field is. See the next equation.
Substitution then gives. See the equation shown. B. If the current configuration consists of n circuits carrying currents I sub n, then see the next equation. See the equation shown. So see the next equation.